All right. Amazing. All right. So yes, welcome to Women Who Code Singapore today. We have Alkesh joining us to describe about, and she's going to go through with us a real-time analytics using Kafka and Flink. But before I start, I would like to introduce a little bit about our organization. So our mission is that we like to empower diverse women to excel in the technology careers. And then as an organization, we have vision. The vision that we have is that we want to ensure that diverse women who are actually historically excluded can thrive at every level in the tech industry. So we do have values. These are the 4 core values of our organization, which actually focus on the mission. We design for inclusion. We advocate for change, and we ensure that we always recharge. We celebrate wins, and we always break barriers. So without further ado, I would like to introduce Alkesh. She is actually an engineering leader at Confluence, as she's also an international trainer, career coach, and author. So without further ado, let's go and start. And I would like to pass the baton to Alkesh to start the workshop today. Okay, thank you. So yeah, I will stop my sharing, and Alkesh, you may start.
Thank you, Stella. I'll start with sharing my screen and let me know if you guys are all able to see it.
Yep, I'm able to see your slides.
Yep. Cool. Let's get started. And before I start, I'll help you with the way I will be talking to you. My screen is here, but I can see you all here. So when you ask me any question, I would like to see your faces. And when I do, I'd move my head here. Okay. I hope that does not create a lot of distraction for you while you're in the learning process. Okay. And then before we start, I'd like to give you an introduction of Confluent. So Confluent is a Kafka company. We started with the core developers who created Kafka from scratch while they were in LinkedIn. And this community in itself, the Kafka developer community, has been created to get developers excited about getting onboarded onto Kafka and Flink. Okay, so this workshop also is part of that activity, and we'll go through some history as well of Kafka and Flink during our session. But before we do that, I want to share this slide with you where you can join the Kafka user group. And in case if you have any kind of questions onboarding onto Kafka or while developing onto Kafka, you'd be able to get ample support from these user groups. Okay. Also, when you onboard onto Confluent, you'd be able to utilize the free credits that we have available for you to go on and try creating topics or get onboarded onto how brokers are, how the infrastructure works, the basic end-to-end pipeline for data use cases as well. Okay. Now, before we start, what I would want to do is a couple of the audience members had shared their background, but I'm going to ask you again to help me understand who here has worked on or learned about Kafka. So please raise your hands. What I'll do is I'm going to actually look at how many of us know Kafka, right? That will help me understand what the level is. And this is how I would want to tune the workshop as well. So quickly, by the raise of hands, who all have learned or worked on Kafka or Flink? So I have Shan here. Who else? I know Emmanuel is a data engineer and he has worked. Then Angeline as well. Who else? Celeste, have you also worked or learned about Kafka or Flink, either of these? Do we have Celeste here? Okay, we don't have any more, but okay, cool. So I think we have the names here. We have Shang, Emmanuel, and Angeline. So what would happen is during the course of this workshop, whenever there would be questions, so these veterans, we call them Kafka veterans. So these veterans are going to get the first chance to answer the questions from the audience. Okay. And then later, if the still my help is required, then I'll come and I'll add to what they have shared. Okay, so this is how it's going to work. We have Shang, Emmanuel, and Angeline. And then whoever answers the questions during the workshop as well, they will all get points. And I have a leaderboard maintained here. At the end of the session, we'll declare the winners of the session as well. Whoever answered the most questions. We good to go? Okay, so I have Shang, Emmanuel, and Angeline. Are you guys up to the challenge? Yes?
I'm sorry, I haven't worked. I'm not yet an expert in Kafka. I haven't worked on Kafka yet.
You have learned about Kafka, read about Kafka?
No, I haven't worked on Kafka yet.
Okay. So looks like the competition has just decreased. We have Shang and Emmanuel now, right? And whoever wants to participate while answering questions, you would all get points at the end of the session. I'd share the winner with you. Okay? Okay, let's get started now. So Stella has already introduced. I'm an engineering manager at Confluent, handling the billing and monetization teams. I have 1.5 decades of experience in cloud native data, ML, and AI kind of platforms. And I've worked with companies like Amazon, American Express, and Paytm. And I'm an author, and also I'm the founder of a service institute called Career Engineering. Okay, so now let's get started with real-time data pipeline. So before we start, I want to basically start asking you this question. What do you understand by real-time data pipelines? And can you share me some examples which you think are driven through real-time data? Over to you now. So unmute yourself and share the examples that you know of.
Does share consider like when I want
Huh?
to trade shares?
Yes.
Because when I saw like trading, I think the numbers keep moving up and down. So I was wondering, is it real time? Should be, right?
Correct. And Stella, you also get a point now. And that's true. Shares is an example of a real-time data pipeline. True. Do we have any more? So some of the data engineering guys who have onboarded onto the data projects.
Shang mentioned camera feeds.
Okay, I can't see the messages here. So speak up if you can. Wait, let me put in the messages as well here. Okay, I can see the messages now.
Yeah.
Camera feeds, correct. RSS feeds, yes. Fraud detection, true. Banking, video, music, event-driven data feeds, that's true. Now, can you help me understand, out of the use cases that are mentioned here in the chat box, which one are the near real-time cases, while which are those which are real-time data use cases? And plus, this would also help me understand if you guys understand the difference between near real-time and real-time data use cases. Yeah. So say music, is that a real-time data use case or is it a near real-time data use case? Music streaming.
Near real time?
Near real-time, true. So out of the data engineering guys, do you have understanding of why did she say that it is a near real-time use case? Any guesses? Yes? It depends. Camera video feeds can also be batch. Correct. Okay. So difference between near real-time and real-time data use cases is, first, for near real-time use cases, it's okay to not have it displayed or presented at the same instant when the data was created. It can have some delay, or it can even have some drops. So for example, when we stream music, it's okay to drop a byte here or there, correct? But if we are doing some account ledger activity, so for example, if there is a debit transaction happening, is this acceptable to have a data drop there? Yes or no? On the chat window, yes or no? No, correct. So we can't drop any data there. Okay, so that's the difference between near real time and real time. Now let's talk about, when talking about near real time data use cases, here are a couple of this situations. So for example, let's say that you're doing a bank transaction. Okay, so somebody, when doing the bank transaction, the bank wants to know during the same transaction itself if the user who's doing that transaction is a fraud or not, or is it does the user fall in a risk category or not, correct? So those kind of logic need to be implemented at the real-time situation itself. Similarly, if there is a product, so for example, the inventory updates need to happen at real time. Imagine you're sitting on Amazon and you're buying a product, and at that time it says that it is available, but just at the after the order has been done, your money has been deducted, and that at that time you see that the order has been cancelled because the product is not available, right? That would not be a great user experience. So all of the updates that need to happen, they need to happen at the real time. Whatever be the number of concurrent users sitting on that particular project at the product at that point, we would want that the update in the quantity should happen at real time itself, right? So these are kind of real time use cases where a single drop of data is not accepted. Okay. Now, what does it mean to have real-time use cases? So when we started with creating such complex online systems or retail systems, say for example, so we needed a software which could actually take the input from one place. So for example, we are ordering a product, and at that time, that order event from the website or the app should actually be able to go to multiple different destinations. Now, is there any way to achieve it? Have you seen such a situation where input from one end needs to go to output from multiple ends? Anyone who has worked on such situations? What have they used? Do we have? Have you guys seen such a situation wherein you have events from one end and they need to go to multiple different sources? Yes, event-driven data feeds are one of the examples. So here, the kind of application or software that existed earlier were, say for example, Redis MQ, or different types of queues were available. Now there is a challenge when using queues for such situations. Anyone who wants to answer that? Emmanuel, I'm giving you a point, or rather 2 points actually, for earlier question as well. Yeah. So anyone who's up for answering this question? What is the challenge with using queues for this situation?
Consistency.
Correct. Delay. Okay. Okay. This would basic reliability. Can I give you a hint? A push and pull versus a pub sub. Anything? When we use a queue, what happens? How does the item is utilized from the queue? What happens when it is consumed, right? So say if one of the sources was using, exactly, it comes out as a FIFO, but when one of the consumer has pulled that data, does the data still stay there? No, right? That data has actually come out of the queue. That is a challenge. So say, for example, the first item that we see here in this list is storage. So say if for storage, that storage was one of the consumer of the queue, then in that case, the event which had gone into the queue would have gotten consumed by storage and it would no longer be available on the queue itself, right? Now, then there were several systems which created solutions for this particular problem, and that's where Kafka came into picture, right? Kafka provided a distributed, persistent event storage. What does this mean is that when we have events created from a source, it could be a order that you're doing on the app, or it could be an event which is coming from your database, right? That can actually be written onto Kafka. Okay. The event would stay there, and there could be multiple consumers who would keep reading from Kafka itself, but the event will stay there in Kafka. Okay, so this ways, what Kafka did was provide a break in between, become the master service which will handle the event storage. Okay, whoever wants to read can read from Kafka without having the danger of missing out on any data. Okay, now what are the top characteristics of Kafka as compared to the other queues that we have available? Okay? That's where the fact that it is distributed, it's not a single system where all your data would lie. It would actually lie on a whole cluster of brokers. Okay, so this way, if one broker goes down, you don't lose that data. The data is still available on the other brokers, and we'll see soon how it happens. Similarly, it's highly scalable as well. Okay, when, say, for example, if we have a cluster of, say, 5 brokers, if we need to increase it, you can add more brokers on it. Okay, and these brokers, when added, they will redistribute the data, and for the consumers and the producers, it would essentially nothing would change from their perspective. Kafka cluster in itself will handle all the complexities of data redistribution as well. Okay, so these were the top characteristics of Kafka, which actually help in making sure that an event from one producer can actually be consumed by multiple other consumers. Okay, now still here there was a challenge. Kafka essentially is becoming a pipe for events to pass through, correct? What about the real-time business use cases that we talked about? For example, fraud, right? Anomaly detection and monitoring the events as they pass. Okay? So that's where Flink comes into picture. So earlier what used to happen is that when we used to run any fraud detection algorithm, we used to actually wait till end of the day, get all of this data in bulk. Either it might be coming from S3 or HDFS. We get this data and then run our, say, daily jobs, bad jobs on top of it. Yes, who all has done this as part of their jobs? For example, using Hive to run jobs, Spark to run jobs, or even a simple Unix or a Linux program to run jobs. So who has done those batch kind of jobs?
Okay.
Raise your hand. Yes.
I think Shang Shang has an question. He asked about what about KSQL?
Absolutely. I'll just answer this question. Meanwhile, okay, yes. So we have few hands raised for bad jobs. Yes. Okay. Now the problem with bad jobs is that the output that you receive, you receive it at the end of the day after your transaction has already happened. So for example, we are running, say, a fraud detection algorithm, and it is run as part of a batch daily job. It runs at the end of the day, then you get the output of it, right? But then the transaction that was supposed to not happen would have already happened because you're not doing this at real-time basis. And how do we get it done? We get it done through stream processing, real-time processing engines. For example, Flink, KSQL, KStreams, Storm, right? Anyone who has worked on Storm as well? Hands raised. I see Emmanuel's hand is raised. Emmanuel, is this raised from the earlier question? Yeah. So these are the examples of engines who can process your streams at real-time basis itself. Now there is a question about KSQL. Yes, KSQL is also an alternate for Flink itself. So these are all stream processing engines in itself. Matter of fact, as for development, for enterprise level projects wherein we need millions of events getting processed at milliseconds or seconds latency, that's where we use Flink. Okay, else otherwise in all possible scenarios you can use any possible combination. So you can have Kafka plus say Spark streaming, Storm, or KSQL, K-streams. Okay, you can use those examples. The only thing is you need to understand how is it that your use case progresses. I have a question. Could you explain the difference between why use one over the other? Okay. Sure. So how many examples of streaming engines we saw? We have Spark streaming, Flink. We have Storm, KSQL, and K-streams. Now let's look at KSQL versus Flink. Yes, definitely. So I have, matter of fact, created projects in both KSQL, K-streams, as well as Flink. Okay. Now, when it comes to KSQL, the benefit that you get is that you can actually get the KSQL DB as an added advantage there. So that's one benefit. The cons that I faced while creating my own project also was that when it comes to some thousands of events, it's fine. The latency is fine. But when my use case grew and I actually needed it to grow up to millions of events per second latency, that's the time where my KSQL did not expand. Okay, so for those such use cases, I would actually want a Flink cluster in itself, which can actually absorb the new scale at which data comes and give me almost the same amount of results. Okay. Then the other part is that K-streams, KSQL, they are mostly libraries in itself. While when it comes to Flink, you would actually need to set up a different cluster. The benefit that it gives is now your Flink cluster, your streaming cluster in altogether is a separate cluster that can be maintained, scaled individually. Good? Yes? Okay. So that's where now we have understood where stream processing engines fit into this whole paradigm. Correct? What they help with is they can do processing at real time, as well as you can tweak them to process at batch mode as well. At both Flink, Spark is anyway created for batch itself. Then these are distributed as well. So when we have a Flink cluster, because it is a cluster of several nodes working together, the tasks are distributed. Okay, so there would be multiple threads of a single task that can run at different nodes as well, at different pods as well. Okay, another question that we have received is, so Emmanuel is asking, can you please explain the difference between Spark streaming and Flink as well? Yes, definitely. Flink we have heard. Now let's go to Spark streaming. Now Spark was created by a developer called Matei Zaharia, okay, Berkeley Labs. What he created was an alternate for Hadoop. If you guys have you guys heard about HDFS Hadoop? Yes, do we have anyone here? Yeah. So in Zoom, there is a feature when you can thumbs up, just like how Emmanuel is doing, or you can raise your hands or show your emotions as well. Right? Yes, so I have, oh, super, nice, great. Since you have, most of you have heard about Hadoop and HDFS, you would remember that the way we used to process data in Hadoop was through map and reduce jobs. Yes, okay. So we used to write map function first, and then we used to write reduce function first. right? And then in between, you will write combiner as well if required. Now, the challenge there was that a lot of data you got to was written onto disk and then read from disk. So Matej wanted to create something where they can actually utilize the computations happening inside the memory itself. That's where Spark came into picture. So he created the concept of RDDs. So instead of the Hadoop objects that we used to use in MapReduce jobs, came the concept of resilient distributed data sets. Okay, they were all residing in memory and persisted when required, right? When it overflows, spills into disk. This is the base concepts on which Spark started. Now, because Spark was working on batch of data, correct? So it was when it came to creating real-time or near real-time use cases, they started thinking of it in this manner that a batch, if it is like this, what would we call this? This much of data. It would still stay a batch. If I reduce it, it will still stay a batch and it will still can be used as a RDD, right? I can reduce the size of RDD. What if I reduce the size of my RDD to one single event? Right? Then in that case, would it start acting like a real-time use case? And it was successful. That's what they started calling as Spark streaming. Okay. Matter of fact, when I also started creating projects 10 years back on the real-time or rather near real-time use cases, we also first utilized Spark streaming. We had to onboard from Yarn to Mesos. Do you guys remember? Spark would only run on Mesos like 8 years back. Okay. So we onboarded onto Scala and Mesos for running Spark streaming jobs. Now the challenge there is that it started acting like a stream processing engine, but when it comes to the latencies that are required, it would still not give us the same level of latencies as Flink gives or a Spark or a streaming pipeline gives. Matter of fact, for many such use cases that I have also developed, Tom would perform better in terms of latency as compared to Spark streaming. Okay, because essentially Tom from the architecture itself was created to handle events rather than micro batches like Spark streaming. Okay. Emmanuel, is your question answered? I saw your hand raised again. Good. Okay. Good question. Now let's move on. So now basically what we have tried to figure out is that how do we solve this real-time use cases plus computations that need to happen on streams at the same instant itself. Okay. Now let's try to see, has this combination been used in the industry? Okay. And how have they used it? So we are looking at a use case at Uber. So this is from a talk that Uber had presented at one of the summits. Matter of fact, Uber, Netflix, they were a couple of the first adopters of Flink and Kafka. Okay, so now you see here, all of this rider app, drivers app, and the map data is actually coming to Kafka. Kafka acts as the event storage, and then this data is going to other engines. So for example, ELK for debugging purposes, we all use, Kibana. Then it is also going for mobile apps, where this is where PubSub comes into picture, right? Something like Redis MQ. This is where the notifications come out for such use cases. Then we have Hadoop kind of use cases wherein this data is processed for historical purposes and reporting purposes. But if you specifically look at the use case for real-time analytics, they have used a combination of Kafka and Flink. Okay, this is Uber's use case. Let's look at another one. This is Netflix. Okay, and if you look here, this is actually a ETL pipeline that you have created. We have a couple of data engineers here, right? Can you guys relate to it? Yeah. So we have multiple different sources of data. This data comes into an extractor. This entire extractor is actually developed using Flink itself. Okay. And there are multiple functions that I use. The data is transformed, enriched, and then pushed on to multiple different sinks. Similarly, one interesting use case, again from Netflix, I wanted to highlight here. Now we have all, when we think of Flink, the first thing that comes to our mind is that it is a streaming engine. But then it is important to note that when it comes to the way you want to process, you can actually tweak it to start collecting data and work as a batch engine itself. Okay, so here they have actually used for Flink for backfilling, which means that if you see on the right side of it, there is a live data coming from Kafka and a backfill data from Iceberg as well. This is the Apache Iceberg from where the past data was stored, and they were using it to process and enrich the data and push it onto Sync for backfilling. I find this use case pretty interesting because this is kind of what used to happen in Lambda architectures as well. Have you guys heard of Lambda architecture? Okay. No? Okay. So Lambda architecture was, initially we used to only deal with data in terms of batch data, right? This is the time when we used to work on big data. We used to call it big data. Most of the processing used to happen in batch mode itself. Okay. Now, when it came to having real-time data also enrich your old data, we started working on figuring out how we can enrich this, use the streams data to enrich our batch data, and that started the architecture that we used was Lambda architecture. So you would have, so if you guys remember, Uber came up with Hoodie. So Hoodie is basically a software which is developed to handle real-time streams on top of your older data, the historical data. Okay. If you guys have not looked at it, then I would suggest you read about it, Lambda architecture. Okay, pretty interesting. And since you, some of you are onboarding onto data engineering, you would be able to understand more the concepts of real-time architecture, the data engineering, how ETL has gone away, right? All of those concepts you'd be able to understand more if you look at these basics as well. Couple of more use cases on Kafka and Flink on production pipelines are from Lyft, Paytm, and Hotstar, wherein the real-time apps data is collected into Kafka. If you look at Hotstar in particular, see apps, from these apps, the real-time video events are going to Kafka as a source, and from there, Apache Flink is utilized for creating the feature metrics as well as the latest counts and fraud detection, etc. These kind of use cases are handled here. And then things like your ranking systems, which are basically your recommendation systems or your personalized systems, they are sourced through the output of Flink jobs. Okay. So these were some of the examples that I shared, wherein this particular combination of Apache, Kafka, and Flink has been adopted across industries which have a very high volume of events being processed at millisecond basis. Now let's go into Kafka. Now before going into Kafka, I have a question. Who all here knows who created Kafka? Who created where? Question? I'm actually going to write who answers this question. LinkedIn. Yeah, Stella was quick to. So Stella, you get another point. Yeah. Okay. And anyone else here? Okay. Stella is correct. Kafka was created at LinkedIn. Anyone who knows who created Kafka? Do you guys remember the developers from the original core Kafka? Yes. Where are the data engineering guys? Emmanuel, we have who else? We have Stan, CEO of Confluent. Yeah, correct. Almost there. Yeah, so you get one more point for that, Stella. Okay. So Kafka was created at LinkedIn, and the initial development was done by three main developers, Jay Krebs, Neha Nathide, and Jun Rao. Okay. And then the next year, in 2011, it became open source. And next year, it got the Apache license. It started to be called Apache Kafka from then. Now, till that point, Apache Kafka was still a software that you could install on your systems, on your servers, and then work on top of it. Jay, Neha, and Jun, they saw a huge opportunity on making Kafka cloud native, so that the manageability part of Kafka can be removed from client's side. Okay, so now Confluent was founded back in 2014 by Jay, Neha, and Jun, the three co-developers. And since then, we have actually become the company to contribute to 90% of the Kafka development, the open source Kafka development, you see. Okay, most of the time there are most of the features that we develop, we keep them as premium, and then later some of the features we open them up to be used by the open source community as well. And that holds true for all of the systems around Kafka that you see: KSQL, K-streams, schema registry, connect, and the huge number of connectors that we support. Okay, so when we work or develop in Kafka, or if there are any Jiras or issues that are created, so those KIPs are actually developed and solved from Confluent itself, and then pushed on to OSS Kafka, open source Kafka as well. Now, interesting twist here when it comes to Flink. So who here knows Flink created and by whom? Yeah, come on, data engineering guys. Okay. Okay, then we'll move to the next slide. So Flink was actually created again as a project done in a lab or in a school, actually, in a college, actually, by in 2014 by Costas and Stephen. Okay, and in the next year, they were able to license it under Apache, and it became Apache Flink. Now in 2016 is when they started a company called Data Artisans, which was focused primarily on developing Apache Flink, okay, and customize and monetizing the products based on Apache Flink. Now, in 2019, an interesting twist happened wherein Data Artisans was acquired by Alibaba. Okay, and matter of fact, I also got an opportunity to meet some of these guys back in 2019 when I traveled to China, where I was with Paytm, and Paytm heavily has a very tight tie-up with Alibaba. And interestingly enough, Alibaba already had something similar to Flink that they had created, and it was called Blink. From Baba, Alibaba's Baba, they used to call it Blink. They already had something, and now that they acquired Flink, they started enriching Blink as well. Okay, and then later, around in the same year itself, Data Artisans was also renamed to Verberica. Okay, so if you want to go look into, so for these guys who are onboarding onto data engineering, go look into Verberica. Now, Verberica is the Data Artisans company which got renamed. Okay, now from Verberica, after the 3 years of contract, the core Flink developers, they moved out, and then they created a company called Emerald. Okay, and the next year, in 2023, this year itself, in January, we started with a bang and we acquired Emerald. So now around 18 of the core Flink developers are now developing Flink as part of Confluent out-of-box projects. So now in Confluent, we have the same founders of Kafka as well as Flink. Yeah, so it's pretty interesting being able to actually provide a product which is now complete in itself, and we want to close the year as well with a bang, with a blast, because we started the year with acquiring Flink, and towards the year we are going to start providing Flink on Confluent Cloud. Okay. Okay, now coming back to the events processing, and we now understood how Kafka and Flink can work together to handle most of the real-time use cases. Let's look at the entire ecosystem, how it will fit into the ecosystem. Yes, this was one of the questions that was raised earlier today. So when it comes to a real-time use case, there are some things which stay same, right? And this is how you would define a typical data engineering project as well, that you would have a source which would be creating data, right? And then there would be a system in between which would collect data, enrich it, transform it, and then push the data onto somewhere. It might be for, say, sync purposes, for example, Hadoop or S3, or it might be for search purposes, Elasticsearch, or lookup purposes like Cassandra, Redis, etc. Correct? Now, how do we get data from a source? So initially, when there were no connectors, the way this used to happen was that, for example, in the projects that we had worked on, right, we used to create a Java producer which would start writing these Kafka events. Okay, they will create these Kafka objects and then start pushing them into Kafka. So we would actually have to end up writing, say, a JDBC connector, which would read from the MySQL or Oracle server and then get that event and then write onto Kafka. Right? So there were applications which were developed, right? And connectors were created every single time whenever we needed to get data from somewhere and push it onto Kafka. Essentially, we are talking about a Kafka producer. Okay, so that's where Kafka Connect came into picture. Okay, we have Kafka clusters and which has brokers. Then we also have a Connect cluster. What Connect cluster helps is that what data needs to be pushed into Kafka, right? It needs to be coming from a source, correct? Now, instead of every single company, every single developer in that company writing their own versions of these producers, how about providing these connectors out of box itself? Okay, so because anyway, if you look at who can be producing data, who produces data? Our apps produce data. So essentially, there would be a application which is creating these events, writing these objects somewhere. Our databases create data, DDL events, right? Similarly, we have Oracle, we have Cassandra. There can be multiple different use cases, or there can be CDC engines as well, like Behaviour, who are creating these events, right? So rather than having everyone develop those applications separately to get data from these sources, Connect started providing connectors. So you have single connectors already available. So there would be a Cassandra connector, a Debezium connector, a MongoDB connector, or a Redis connector that you can use and tie it up with your Kafka cluster, and they would start reading the data from the Cassandra cluster, for example, and push it onto Kafka. Right? Then the other side of a data engineering pipeline or a real-time pipeline is where the data getting written onto somewhere. Again, this is where a lot of consumers needed to be created. We call them Kafka consumers. Yes. So Kafka Connect can actually provide these connectors out of the box. So all you need to do is there is a Connect cluster. It would have a URL. Okay. You need to call that URL through a REST API and provide the input as to, for example, I need my data to be pushed into Elasticsearch. Right? So I would provide in my URL, I would provide that this is my URL, this is the cluster IPs of Elasticsearch where the data needs to go. As simple as that. Okay. Now we have talked about source and sync, and Kafka Connect came into picture. Similarly, to process these events at real time, there are options also available. For example, KSQL, KStreams, and Flink. Right? So this combination can actually help create an entire ETL pipeline or maybe real-time microservices pipeline, which can help create near real-time or real-time use cases. Now let's quickly go through Kafka, understand the basics of Kafka, and this is where I'll be asking a lot of questions. So if you want to get points, this is the time when you get started. Okay. Now let's start with how do we actually install a Kafka cluster? What is a cluster? When we talk about a cluster in Kafka, a cluster is actually a group of brokers. Okay, so your brokers are basically multiple different machines on which a Kafka daemon is running. Okay, all of the data which is written by producers get written to these brokers, and the consumers, they read the data from these brokers in themselves. Okay, there are multiple brokers, which means that your jobs, your data that is written and processed, it is distributed, okay, and replicated to give HA functionality as well. Moving on to topics, the way data gets written. So for example, when we write a Java code, we create objects, right? Objects travel from here and there, they get processed. Similarly, when it comes to Kafka, these are written as events, okay? So an event can be defined as a group of key and value. So there would be a key. So for example, if it is a user event, we can see user ID can be the key, and everything related to that user, be its name, address, mobile number, history, etc., that can go as the value. This key and value gets written onto Kafka topic. Okay, so what is a topic? Topic is basically a file. Okay, so when the way I explain topic is, when you look at topic as a file. So topic is not a in-memory construct, it is a file construct. So when we talk about topics, they are actually logs of events. You see here, topics are basically durable logs of events. Why do we call them durable? Because even if one fails, you have the copies of this file available on other brokers as well. Okay? They are persisted. So unlike queues, where you write data to queue once, and if somebody does a pull using FIFO, the event comes out and the event is no longer persisted on the queue. Right? Unlike that, in Kafka topics, your event is always there in the topic. Okay, and when we write onto a file, we always write that file in an append only mode, so that to make sure that our data doesn't get dirty. And these are the kind of constraints that Kafka has put around to make sure that it is actually able to handle all multiple different consumers without them getting impacted. Okay, so all the events that we write, they are append only, and they can only be seeked by an offset. They are not indexed. Okay, why do we say that they cannot be seeked by an index? They always have to be seeked at the end. Anyone who wants to answer this? Yes.
Is it because it's key value pair?
Sorry, can you come again?
Sorry, is it because it's a key value pair every time you put the topic inside?
Okay, somewhere close. Let's look at it in this way. Say this is a file, correct? Now, when we write to file, do we write the file data randomly versus if we write that data in a sequential manner? Which one would be faster? Which one would be faster when it comes to writing data to a file?
Sequential.
Sequential, right? And why do you think so? Emmanuel has answered sequential. Correct. A point goes to both Stella and Emmanuel. Now, help me understand, why do you think sequential is better at writing if you want higher writing speed as compared to random?
Easier to find because you know where the exact location is in a way.
So let's try to think of it as easy to store in partition and read. Okay. Let me help you understand how data gets written. Okay. So basically, all of this data is getting written to a disk, correct? Which means that there is a disk which is rotating and you have a writer. Okay, now that actually needs to go to that place, okay, do the seek, and then write the data there, right? Tap, 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 tap. This is how bytes are written, right? Now, if it was random access, and then if you are writing data, so one data is written here, another is written in another sector, some other data is written somewhere else. Would that be faster, or rather, if it only needs to go to one sector at one point and then write the date, all the other events which are coming in the same sequence, tuck, 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 right? The seek time here is reduced, which means that when it comes to writes, your data would be written faster, right? So that's why when it comes to Kafka, the constraint that has been put is that all the data gets written sequentially, okay, and it is written in append only order, okay. When we talk about append only order, it means that when we are writing on a file, right? If we want to go and write somewhere in between, can we do that? No, right? All of the rest of the file will get updated, correct? So because Kafka logs are actually files, all of the data which gets written, it gets written at the end of the file. Right? We have all created buffered writers and written onto file at some point, right? So this is the same example in which Kafka also works. Events are immutable. This is again a constraint that has been put. Can anyone help me understand or want to answer why events have been kept as immutable? Why can't we actually update them? Anyone? Loss of data? Yes. Correct. And consistency issues and data corruption? Absolutely. So both Emmanuel and Shang, you are both correct. This is the reason why we have not let events to be mutable. Whatever event stays, it stays. This way, say if one of the consumer has already consumed an event, right, which means they have processed something, they don't have the ability to go write some data and update it as well. Okay, it's a log and append only, correct? That also sets a constraint. And this way, Kafka was able to ensure that whatever consumers want to read data from the topic, the data would be consistent to what was written by the source as well. Okay. Now, my question to you all is, if it is a file, right? And if I say, for example, I was writing onto a file, right? At some point, it would fill up, correct? Now, how is that situation handled in Kafka? Or maybe say, let's say in any other project or product that you have worked on. Let's make this an interview question. Retention period, yes. So it means that what retention period means is that we only store some data at a certain for a certain duration, and then we let go of that data. Okay, so another way it is also done is so using topic compaction. What it means is that if there is, say, you're looking at order status, right? So if order status, initially when you created that order, it is at initiation stage, and then later on when it moves further, it is, say, order is accepted, and then it is in logistics, and then the order is in delivery stage, or it has delivered or refunded, right? There are multiple states. Now, if we only want to maintain the latest snapshot of the state, then in that case, we can also enable topic compaction. What would happen is that for a particular key, the latest event will be stored and the others would be removed. Okay, I have a query from Shang. I have a question related to Kafka streams, reading implementation. Yes, absolutely. So during the start of the session, we had shared a Kafka consumer group. Either you can post your questions there. We also have Anna all in the meeting, or you can directly write to me on Alkesh Chauhan at LinkedIn. Okay. Okay. Since we are nearing the end of the session and there was a lot to cover, I can continue. I still have 15 more minutes to continue if you guys want to. And in case if you need to drop, feel free to watch WWC for further events, I'm sure would be happy to organize similar such sessions again. Okay. Okay. So now we were talking about compaction and data retention as well. Right now, there, let's see this. So data retention can basically ensure that the data is the file doesn't grow beyond a certain point. But what if? So if I have this file, how many people, how many writers can write onto this file at one point? At one point, atomicity level. Okay. And if I talk about one file being updated, it can only be written by one writer. Only one producer can write onto it. But if your applications, which are basically the producers, they grow, then you need them to be able to increase their throughput, right? Which means that they should be able to write more data in the same duration. So what happens, the way Kafka handles this is that a single topic, right? This was a single topic. Instead of having this as a single file in itself, we break it down. Okay. So what happens? We create partitions as part of a topic. We create partitions, and you can actually create multiple such partitions and tweak it as well. And with partitions, when there are producers which are writing, the events that will be written onto these partitions would go through a algorithm called hashing algorithm. Okay, random access or through a simple hash, they would be distributed across the partitions. Oh, there is a question. Will compaction give me history data for backfill if it stores latest transaction? Okay, yeah. So to answer this question, if you want historical data, then in that case, you would not use compaction. Why? Because during the compaction process, for a particular key, so for example, say the key was Emmanuel, all of the events that were received earlier will be removed, and only the latest event for Emmanuel will stay. Okay, so this way, of course, the earlier data would get removed. You would be able to free up space on your broker. Now, if you have a requirement for historical data, then in that case, you would not set compaction in your topic. Okay, but you would rather set, say, retention period there. Okay. And if you have this longer historical data requirement, then in that case, you would go for HDFS or S3, where all of this data from Kafka would get stored into HDFS. Okay. We did see a lot of use cases from Netflix and Uber as well, Hotstar. They were all putting their events onto HDFS or S3 in one form or another. Emmanuel, does this answer your question? Is compaction at partition level? How does different consumers read it? Okay, compactions. Yes. So compaction actually not only happens at partition, it actually happens at segment layer. So inside a partition also, the data is actually written in smaller chunks, and those are called segments in Kafka. Okay, this is like advanced level. So when the data is written, imagine that every single file, so segment is actually a file. Let me help you understand, explain through this way. So when we write logs, or when some of our applications are writing data onto some files, do we write onto one file, or do we actually create multiple files? So say file _0, file _1, and then we keep them on a rolling basis, right? Correct? What do? If we have to remove a file, we actually remove the last file that was written. Similarly, compaction also happens in the same fashion. So the data is actually written into segments. These are kind of rolling segments in a way, you can say. What happens is that the oldest data gets removed first, whoever's retention period has been reached, and we'll look at it in some time. When we talk about partitions are stored on brokers, okay? And they are actually stored across multiple brokers. So you see, this topic say had 4 partitions, all of these are stored on separate brokers. So if one broker goes down, only some of your data is lost, other data is not impacted, okay? And Kafka actually handles this situation also by making it HA, and we'll look at HA as well. Now, one question could be that how do producers understand which partition they have to write to? Correct? And the way it is handled in Kafka is through these partitioners. Now, the partitioners by default logic is that it's a simple hashing function of the number of partitions, and that's how the data. So, for example, if I have a producer, say it's a Java application, it's creating an object. That object actually needs to be written into Kafka. What would happen is that the producer level itself, the API that we have used for Kafka, it would implement the logic as to which partition it should go to by using a simple hashing function as it is here. Okay. Now, we saw that all of the partitions are actually created and stored on brokers. Now, what happens when a machine goes down? Do we lose onto that particular partition which was stored in that broker? We might, right? So to handle those scenarios, that's where replication comes into picture. So for a single partition, there would be multiple copies of that partition stored across different brokers. So for example, let's see here, there is a partition 0. For partition 0, the leader is stored at broker 1. The broker 2 and broker 3 contain the copies of it. Okay, all the data would be written and read from the leader itself. Okay, so when a producer is writing data, it would always write to the partition which is the leader, the copy of the partition which is leader. Okay, all the other copies would be copy, right? They would not be used for reading purposes as well. Whenever a consumer is reading, he'll be reading from the leader itself. Now, this is where an interesting question comes up. Why does Kafka implement read and write in this fashion? Because, can you help me understand how JDBC handles this? So JDBC also has, if you look at MySQL or Oracle, they also have a master and slave concept. Correct? They are also created to make sure that there are always copies available, replication purposes and persistence purposes. Right? There, all the writes happen onto the master, but the reads happen from slave, the standby. Correct? What is the problem in in that particular scenario if we read from the slave or from the copy? Who can answer this question? Yeah. Fault tolerance. Yes. So fault tolerance is when one of your system has went down. So for example, to handle fault tolerance, this is where they have implemented master and slave copies. But there is a challenge in implementing fault tolerance in that way, having the data written onto the master but read from slave, versus a situation like Kafka wherein all the data is written onto the leader and the readers also read from the leader. They don't read from the copies. What could be the rationale behind it? What do you guys think? I see read-only operations are less impacted. Yes, in both the situations. Yes. Have you guys heard about CAP theorem? Anyone who has read or heard about a CAP theorem? Yeah. So in CAP theorem, what it says is CAP. This create a triangle. Okay. What CAP theorem says is in situations of partition fault, for example, what does partition fault means? That inside your entire cluster, one or two of those machines have gone down. This is called a fault. Now, in such situation, how does your system behave? It can either provide you availability, A for availability, or it can provide you consistency, C for consistency. So CAP, the theorem says that in case situations of partition fault, either your system can handle availability or consistency. Okay. So now from this understanding, let's look at Oracle or MySQL servers. All the data is written into master and read from the slave. Now, what happens when a partition fault happens? Say you have a client which was connected, which was writing to your master. Okay, it was writing to master, but whoever, say it updated our data, say who do I pick? Say we have George here. George, say George has $100 in his account, and it was actually updating it to $1 million, right? He was going to get super rich. But what happened? There was a fault, and because of which the data could not get updated onto the slave. Okay, so if somebody is reading from the slave, what is the data that they would read? Would they read $100 or would they read $1,100,000? George, what do you think? It would be, oh, we don't have George responding. Okay, the data that would be read by the consumers would be the $100. Why? Because there was a fault, and the Oracle systems or the MySQL systems are actually built on to handle availability. That if there was a producer writing to Oracle or reading from a consumer reading from Oracle, they should not face any break in the connectivity. Okay, so that would not break, but they compromised on consistency. Okay, this is the way they were designed. MySQL and JDBC servers are designed in this way. But when it comes to Kafka, Kafka compromises on what? Availability, but never compromises on consistency. Okay, so Kafka says either you the data that I'm reading from Kafka, so as a consumer, if I'm reading from Kafka, that data should be 100% correct. Either I read the 100% correct data or you don't give me any data at all. So Kafka believes in making sure that whatever you're writing onto Kafka is the same data which gets read by consumers from Kafka. And to maintain that, Kafka compromised on availability. And they said that all the data would be read and written from the leader itself. Okay, so this is where, in terms of the CAP theorem, while Oracle and MySQL servers, they fall on the availability side, Kafka falls on the consistency side. Okay, we have already crossed a lot of time, so I think we would have to take a break here, but I would leave you guys with a question here. Okay, right? Now the question here is, you have now read about CAP theorem, you have understood about Kafka, you have understood about how other systems like JDBC and Oracle implement CAP theorem. Now my question to you is, what about Cassandra? Or what about MongoDB, Elasticsearch? Okay, pick up any one distributed architecture and tell me what place they fall in the CAP theorem. Okay, so what I'll do is I'll write the CAP theorem, the tag here, CAP theorem. Okay, anyone who works or want to work on data should know CAP theorem. This is how every single architecture is based on. Okay, and I'll leave you with this question. Pick up any one single architecture which you have worked on or read or are excited about reading. Okay, it could be a database, it could be a search platform, it could be Redis, it could be your Kafka or Spark streaming, any architecture, any distributed architecture. Let me write it here, any distributed architecture. Okay, and find where does it lie on CAP theorem. And come back to me on this. You have my LinkedIn ID already here, and I would love to know which one of you guys have looked into it. Yeah. With that, back to Stella, and I'll stop sharing my screen now.
Hi, Alkesh. I think there's one question by Kevin. He's asking whether ELT use case used for Kafka streaming.
Oh, this is the bread and butter for Kafka. Okay, ELT is extract. So we know about ETL, right? ETL and ELT now have become very intermingled. ETL is extract, then transform this data and load this data. So for example, all of the batch systems and batch applications that we used to write, right? We used to extract the data, correct? So for example, if I'm writing a Spark job or a Java application, I would get that data. I would transform this data, right? And then I would load this data onto somewhere else. Okay, this is what we call as a ETL, extract, transform, and load situation. When it comes to ELT, that's where the brilliance of Kafka and Flink comes into picture. So ELT says that extract the data, okay, and then load the data and then transform the data. What it means is that there is a place in between wherein this data is actually stored somewhere, right? And how do we store the data? Through Kafka. So all those events which you are extracting, say you have implemented a CDC pipeline, okay, change data capture. You're capturing all these events from databases. All of the events are actually stored inside your Kafka, okay? That's where the data gets loaded and then transformed. So for example, say you are running a Flink application, which is transforming this data, okay? Say you had orders coming in, you want to transform this data with their mobile, the user information, the address information, etc. Right? So that transformation happens in the streaming application, and then this data again gets written into Kafka. So this way, ELT versus ETL, both the application, both the type of use cases are actually the bread and butter of Kafka and Flink use cases.
Oh, that's something that I've learned today. ELT, never really heard about it. But okay. Hey, folks, do you have any other questions for Alkesh?
So in case if you have any questions, let me do this. Let me actually share the screen again with you, wherein you can take a screenshot and reach out to me or Anna in case if you have any questions. So feel free to take a screenshot here.
Thank you, Alkesh.
Yeah, and reach out to me on LinkedIn at Alkesh Chauhan. Okay, and I'd be able to answer your questions.
Amazing.
Okay.
Yeah. And
it was great talking to you. Yes, Stella, go ahead.
Sorry. Just before you guys leave, though, if you could actually leave us some feedback with regards to the event so that we know what will be the topic that you guys are interested next, that will be great. And thank you so much for your time, Alkesh, spending this evening with us, and have a good weekend. No, have a good week ahead.
It's just a Monday. The Monday blues are definitely.
Yeah, I thought it's gonna be weekend. I was like, no, we can just end yesterday.
Yes, it was great interacting.